In this video, I'm going to explain everything I know on area and volume problems on the SAT. If you want to know why you should trust me, I've personally scored a 1550 on the SAT. I've helped hundreds of students improve their scores already, and I'm working on making this channel the best free SAT channel on YouTube. The thing with area and volume problems is that they look very, very simple on the surface. It's like if you watch a movie like Obsession, like it looks like it's a very basic, simple concept, but you really quickly realize that there's a lot more to it than you maybe thought initially. Like if you watch Obsession, you start to realize, okay, this isn't just a movie about some random wish. The key thing you need to know about this is how each of these work. Now, when I say area, I want you to think of it basically like this. Let's say you have a pancake, and you're trying to think to yourself, how big is that pancake? That is literally what area is. It is put simply, the area within that pancake would be considered the area of that pancake. And so this thing works for any kind of two-dimensional shape. When I say two-dimensional, you can think of it like Super Mario Bros., the original one on the NES. It's something where it's just like a flat surface in front of you, or like a pancake. So if I were to draw this would also be a two-dimensional shape. I could draw this as a two-dimensional shape, and the interior of each of these would be the area of it. Surface area works slightly differently. Surface area works for three-dimensional shapes. Like if I was to draw something like this, think about it like Ocarina of Time on the N64. So more dimensions to it, put simply. So this would be a three-dimensional shape, and the surface area of this is essentially the area of each of the different faces of it that is exposed to the outside world. Keep that in mind, exposed to the outside world. That's going to be important a little bit later on in this video, but all you need to know right now is that, for example, for this cube, it would be the area of this plus the area of that plus the area of this, plus there's three other sides to this cube on the back of it that we could not currently see, but that are there. So we'd add all of those six together, the areas of each one, and that would be the surface area of this cube. And of course, this works with any three-dimensional shape. We could have this here a cylinder, and the way this would work is we would take the area of the middle part of the cylinder, like this whole thing in the middle, then we would add the area of each of these two circles on each side. And that together would be the total surface area of the cylinder. We could have any shape you wanted to as well. It could be a pyramid, it can be a cone, all this stuff. And the last thing you need to know with all this is then volume. Volume is also for three-dimensional shapes like this, but it just works slightly differently. The way volume works is basically how much water you could put into that shape without it overflowing. So if I was to take this cube and I was to fill it with water, we would basically be seeing how much water can we actually put in until it eventually overflows and everything falls out. That is what the volume is, the amount of water. And that may sound like kind of a weird way to describe it, but actually it's pretty much the best way you can, because that is literally what it is. It's the amount of space contained within the thing. For this same thing, if I put water in the cylinder, how much water could we put in until it eventually overflows? That would be the volume of it. So now you know each of those three things, but how do you actually use it on the SAT? Well, thankfully on the SAT, you get this formula sheet. This is unbelievable. It's crazy that you get both Desmos and this formula sheet on the SAT, but yes, you do get this. So this gets a lot of the information that I just went over on it. You can see all these different shapes and how you'd find the area or the volume of each individual one. However, you may notice that there's one thing that is definitely missing from this list, which is surface area. So that is the one issue with this thing. They don't actually tell you any of the surface areas for any of these shapes. So when you have a surface area problem on the SAT, you're going to have to be able to use this exact logic that I gave up here. Well, not the volume thing, but the surface area thing, and then use that to figure out on your own what the surface area of that object would be. We'll see a couple of examples of that in a second, but it's actually not as bad as it may seem if you actually know how this stuff works, which you now do because you've watched this video. The way that most of these problems work on the SAT is they give you some information and you have to make an equation based off of the stuff shown in this table here, or off the surface area stuff. So for example, for this one, you have a right circular cone with a volume of 216. The height is that, and it says, what is the radius? So first we have to look, what is a volume of a right circular cone? Well, as shown in here, a cone would be this thing here. So 1/3 pi r squared times h. So like that, 1/3. And it says that would be equal to 216 centimeters. So I can say equals to 216 pi. In case it wasn't already obvious, pi is just this random, like, crazy number that somebody came up with a bunch of years ago. You can write it on Desmos just by writing pi, literally that, and it shows as pi. So that's what I'm saying when I say pi. Okay, we have this now, and then it says the height of the cone is 3 times the radius of the base. So you can also put in this information as well. So I can literally go ahead and erase that h and make it, let's say, make it red now. And then I can say r and then 3 times r, because it's saying it's literally equal to just 3 times the radius. So there's no reason why I can't just put that there instead. And so now we have this full equation. And if I pull out Desmos here and just put in this exact equation, you can see here they give you the answer, which would literally just be 6 for this. So the answer for this one must be 6. Pretty simple what I just did there. Now that you know the formulas, I'm just putting it in and I'm using Desmos to find what the answer must be based off that. Here's some more examples. Let's say you have this here, we have a triangle, and we don't have actually the question here, I forgot to put it in there, but they're asking you what is the shaded region? What is the area of the shaded region? The way we could do it for a problem like this is first, let's just find the area of the total triangle, then let's subtract the area of the smaller one at the top, and then whatever is left must be the shaded region. That's the rest in here. Area and volume are both addable, subtractable, like that. So if I was to go over back here again, what is the area of a triangle? It's 1/2 base times height, with base being this thing at the bottom, height being the place at the bottom to the top. So if I was to write it for this triangle here, we could say 1/2, and then the base of this bigger triangle, we go 1 to 12, so 12. And then the height of it, we would just look at this point of the triangle and then go straight down. So we can see here, this would be 9, so just 1/2, 12, 9. If I put into Desmos there, I can see 54 be the answer. And now all I need to do is just find what would be the area of this smaller triangle at the top. So pretty much similar stuff, 1/2, and then the base of that one would be 1, 2, 3, 4, so 4, and then multiplied by the height 3, so that time it would just be 6. Then I can just go ahead and do 54 minus 6, so answer is 48. So this thing here must be 48 by extension. Here's a simpler one. A right triangle has legs measuring 9 and 12. What is the area of the triangle in square units? How this would look if I was to draw like that, when it says legs, that means this would be 9 and this would be 12. This here would be the hypotenuse because that's the longest side of the triangle. So again, 1/2 times base times height, so 1/2 times 9 times 12. Same answer as the other problem, 54 for this. In case it wasn't obvious, for triangles, when you're finding the area, this means the same thing as the base here, and this would mean the same thing as the height here. Triangles are kind of crazy because none of these specifics really matter too much. As long as there's something that's a base and something that's a height, it can work out. So keep that in mind. Here's another one that's going to require an equation. So we have a right circular water tank with an interior radius of 5 feet, and it's currently filled with water to a depth of 12 feet. It says it can add 600 pi cubic feet of water before it is completely full. So this is going to take a pretty in-depth equation here. So circular tank, that would essentially mean that this is something like that, like a cylinder. So pi r squared times h would be the volume for this. So we can go ahead and write that pi r squared multiplied by h. And then let's go ahead and fill in each of these with the stuff that we've been given. So we first get given that it's 5 for the radius. So I could put in essentially 5 there for that. And then it says to a depth of 12 feet. That's the current height of it. So I could put in there for that, I would say 12. And now the other information they're asking is they say that you can add 600 pi to it, and then only then will it actually reach the top of the thing. So let's just go ahead and first solve this. So we do pi times 5 squared times 12, and then we add 600 pi to that. So we get this 2827 number. So that would be what it equals to. But that would not be the answer to the thing, because it's asking us what would be the interior height in feet of the tank. So now we can make another equation using this exact same thing. Because remember, pi r squared multiplied by h, and that's equal to 2827.43. I would now go ahead and take this and I can just make another equation. So we know already that it has to be 5 for the radius because that is how it was before. That never changes. And so I can go in here, put 5 down for that, and then just solve this equation. So the answer here, we have 35 point like a bunch of 9. So that basically is trying to say 36. So therefore the answer here would just be D. In case it was not obvious already, the radius for problems like this refers to when you have a circular object, the distance from the middle of that object to the edge of it. So if we have a 2-dimensional circle like this, the radius would be that, how far it takes to get to this piece on the edge. Or if we had a cone like that, it would just be when you take one of the bottom pieces, the same exact thing, how much it takes to get from the middle to the edge over there. This one, we have a rectangular flower bed with a length that is 10 feet greater than the width. And then we have a uniform path of x feet that is surrounding it. It's forming a larger rectangle with a perimeter of 88 feet. So this is where it gets a little bit harder because now we don't just have one equation, we actually have multiple equations shown here. The first one that we're getting here is that basically it has a perimeter of 88 feet. So 88 would be equal to whatever the perimeter of this larger rectangle is. Now, I haven't gone over perimeter yet because it's not really that complicated, like it's just a pretty simple thing. But basically this refers to the length of each of the sides of a 2-dimensional shape. So for this here, we would just take all of this on the outside, add it all together, and that'd be the perimeter. So what this really means then is that we have, let's say this is the length of it. So basically length plus 2 times x, because we have pieces on each side. So 2x plus length. But then don't forget, that's the first one over here. We have another side, the exact same on the bottom. So let me just add another thing to that. And then I have to go ahead and do the same thing for the widths of each. And each one is going to work the exact same way. We have these core width in the middle, and then we have pieces on either side we have to add. If this doesn't make sense, feel free to leave a comment on this video. I try to respond to every single comment, so I'll get to it if you ask me. Now, this is good for the first equation, but there's one key rule that you need to understand for these kinds of geometry problems. And this is true for all of SAT math, but it's especially true when you have a problem like this. Basically, you need as many equations as you have variables. I talk about this all the time in my Desmos videos on this channel, but here's just another way to look at it. In this example, we have both x, L, and we also have w. So we basically have like 3 different variables here, but we only have one equation. So we have 3 variables and only one equation. That means this thing would be impossible to solve just on its own. So we have to find a way to either reduce the amount of variables here or add more equations. So we need to basically make it so it's like the exact same amount. Like it has to be at least like 3 and 3. Or if we were to reduce the amount of variables somehow, we could say something like just 2 and 2. But there cannot be a mismatch between the two. If there is, it's not going to be able to be solved, at least if there's more of the variables than there are equations. So one way we can reduce this is if we were to put in some of the other information from the problem. It says here that the length is 10 feet greater than the width. So if you think about it, you don't actually even need to put anything in here for the L. We can just completely get rid of that. And instead we can just replace both of those by saying 10 plus width. So 10 plus width there, and then 10 plus width. That should make sense. That's literally just what the length is. It's just another way to say it would be 10 plus width. So that's good. So now we are down to only 2 different variables, which are x and w. So a little bit better there, but we still have only one equation. If we're looking at the tally here, we have 2 variables and only one equation. So there's still a bit of a mismatch here. So we have to find a way. Let's just go ahead and add another equation. And a good one to add would be the area of the path being 288 feet. So I can say here 288 is equal to the area. In case you're not familiar yet, I can go and look over here. For a rectangle, it would be length times width. Pretty simple. It's like the easiest one for that. So I can just take what would be the length of this. Well, as we already said, it would be basically just like one of these pieces because yeah, it's 2x plus the whole 10w thing. And then let's just multiply by the width, which would just be exactly this. But what you may notice is that I actually made a mistake here. 288 square feet is the area of the path alone for this. What we have here is the area of the entire thing altogether. So what we can basically do is we can just say this would be the area of the path and then add back to it the area of the stuff in the middle as well. What that would equal to is just length times width for the middle thing. So we can just say here w times, it would just be 10 plus w. Okay, so that we don't add any kind of other variables here by doing that. It's a pretty simple change. All we're doing here is we don't want to just use the outside path. We're also adding the inner path as well. Add them together, and that should be the total area here. What I can do next is just put this entire thing into Desmos and then solve it through that. Keep in mind here, I replaced w with y just because when you solve it easily like this, it doesn't let you just put in a number like w. Otherwise, it can give you an error like that. So I have to put y in here, but that's fine. So then all we have to do next is just see where they intersect in the graph. I'm going to have a Desmos video coming out pretty soon that's going to go a bit more into depth on how this works, why this works, all that stuff. But just know it's the intersection point for the solution for a problem like this. The question that it asks here would be the value of x. So we just have to see here what would be the value of x. It says here it would be 4, 9. So 4 would be the answer here. I know I kind of just taught you area and volume like a second ago. I'm now immediately throwing you into the deep end with a problem like this, which is really hard. But actually it's useful to understand because all the exact things I explained earlier on in this video just apply in a slightly more complicated way to this problem here. Same thing here about area, adding different areas together, setting up equations. It's just doing it with 2 rather than 1. If you have any questions, feel free to leave a comment again. One more thing with area specifically, you can have these situations where you have a shape within another shape. It's going to look something like this. We have a square here within a circle. And when you have something like this, it may ask you what is the area of one thing, what is the side length of one thing. The big thing you have to understand here is that to solve a problem like this, you need to find something in common between the 2 shapes. So for this right here, probably the most common example you'll see, one thing that could be in common is the diagonal. if we go have a line down and show the diagonal of this square, this diagonal would both be the diagonal of the square, and it's also going to be the diameter of the circle. If you want to know more about diameters, you can watch my circle video. I just posted it as the previous video on the channel, but that is what would be the case. And one thing you may also know is that this splits this square into two 45, 45, 90 triangles because they both have the same sides over here. So that is basically the definition of a 45, 45, 90 triangle. So if we have something like this, the diagonal of AD is 7 here. It says, what is the length of each side of the middle square? So 7, and if you know about 45, 45, 90 triangles, 7 must be equal to x, if this is x, multiplied by square root of 2. Therefore, x would have to be 4.95. So therefore, the sides of it are 4.95. 45, 45, 90 triangles is also not something I've discussed in this video, but I will make another video on this for sure pretty soon. And also, if you just want to check, you can see here, this is one of these special right triangles. So it's also on the formula sheet. It's just this right triangle that can appear when you have two sides are the exact same and one side is a bit bigger. So a square would match this exactly. We have two sides that are definitely the exact same because it's a square. So that's that. 4 different formulas I have here real quick. This one is the surface area of a cylinder. This one is the surface area of a sphere, like a 3-dimensional circle. This one is the surface area of a cone, like a birthday hat type thing. And then finally, this is the surface area of a pyramid. If you want my honest recommendation, I would suggest memorizing all of these 4 formulas. And I know you may be thinking like, oh my gosh, that's so much I have to do. Like, how am I supposed to memorize all this? First thing I will tell you is this is really important because on the SAT, you do not want to have to be fumbling through all these different formulas, have to think, which formula do I have to use? How do I make the surface area of a cone or something crazy like that again? You don't want to really have to be doing that. So it's good to memorize these. In fact, cylinder surface area happens all the time. It's really good to have this memorized. Second thing though, it actually is literally not that hard. And I can prove this because I actually did it myself one time. What I did to memorize these 4 formulas was I just had a piece of paper, I wrote them all down, then I did not look at them again and try to write them down again. It was hard the first time, but then the second time I got a bit of it, and then the third time I really got it, 4th time I was like perfect at it. So it literally can take as little as like 5 to 10 minutes to do this. I would say 5 to 10 minutes is worth it for having the chance to get a question right that you typically would not have been able to get right. This is definitely especially useful for this one and this one. These are the kinds of things where, yes, maybe there's a logical reason why it works. Maybe you could think about it, but like realistically, you probably are not going to be able to realize why the surface area of a cone or of a sphere works the way it does because it is just kind of weird. So memorizing this is very useful. Cylinder and pyramid does definitely help as well, though you can figure this out pretty much logically, kind of like I did for this problem over here. Now that I got that out of the way, what if we glue stuff together? You can have these honestly kind of stupid problems where they take multiple shapes and then they put them together like an art class, and now you have this multi-shape. Now this is pretty simple. Pretty much everything about this is quite self-explanatory. Like the volume of the shape would just be twice the amount of the original because now we could put 2 times as much water in it if we were to try to fill up this entire thing. Cube, you can only put so much water in it, but this one you can put in a bunch of water, twice the amount as the original. Okay, but what about the surface area? This is where the foreshadowing comes in. I mentioned to you earlier that's only the exposed sides of the shape that you use for the surface area. So that's where this matters. Because in this thing here, we had like 6 different sides of each one of these cubes. But now each cube basically only has 5 exposed sides. Now, if this doesn't make sense, what I'm talking about here is the one that I have in red in the middle. This whole side has basically been taken away from the equation. It's been removed from the rest of society like a problem child. And so now you cannot see it at all. So this would be not included anymore in the surface area for these cubes. If you understand what surface area is saying, this should make a lot of sense. If you don't, then you might have to understand that this is the case. And then if you have a situation like this, you can use systems of equations to figure out what the answer would have to be. So you could have something like this. 2 rectangular prisms each have a height of 60 centimeters. So if I was trying to write this, I could say it's something like this. So yeah, like that. And then the height of this would be 60. We have 2 of them as well, and both are 60. Now, they are finally glued together along a square base. So basically what this would mean is you put this one on top of that one. So hopefully that makes sense. I know it's getting a little bit confusing here, but yeah, like that. And then it says the resulting prism has a surface area of 2513K, and then was a silent. Okay, so let's first think about what the surface area of one of the things would be. Again, not on the formula sheet, but let's just say, let's take one of these different rectangles. If the height is basically the top to bottom, if this is the length and this is the width, what are all the exposed faces? This is actually like slightly more confusing than it may seem, but it's really not that bad. The first thing is we have a thing at the bottom and a thing at the top, which is its length times width. So we could just say 2 times length times width. Then we have things on the side, so width times height, 2 of those as well, so 2 times width times height. And then we also have 2 times length times height, essentially, because we have the ones on this side as well. Pretty good here. You could include this as one of the formulas to memorize if you'd like to. It does make it a bit easier, I'll be honest. Okay, so we are left with this expression here with all this stuff, and it is going to be equal to k, whatever k is equal to. Now, like before, you're trying to reduce the amount of different variables you have here just to make it a bit easier. Let's think how we can do this. The first one is we have a height being 60, so I can just erase all the heights and just make those 60 instead. So really easy, one variable out of the way automatically. Second thing it gives you is that it says here that they have the base that is a square. So what that would mean is that the length and width is the exact same, so I can also just get rid of all the different lengths and just replace those with the widths. And this is pretty good. We now only have 2 different variables. That's probably low enough. The second one is we have the thing here, they add them together, and now the new surface area is 2513 times k. Now, what about the surface area of this? Well, the simple explanation for it would be that it would just be this thing times 2. So like that basically, but remember the rule I just told you before about the side that's now hidden. So basically what you can think of this as is you're taking one base away from both of them. You know, one base, you don't get that base. So the way I could write this is basically if I just remove 1, so I just make this 1 essentially instead of 2. So pretty easy. That's just a very simple way you can think about it. If you wanted to, you could also just think about it like, I don't know, just remove this 1 entirely, just like, this times, this is just one of the sides. Doesn't really matter. All that matters is that it's now 1 rather than 2 for this because we've lost a side. And now we have 2 things we can put easily into Desmos. We have this with the widths and this with the Ks. Pretty easy stuff here. Just so you know, to make this a bit simpler, and because I was worried there might have been some issues with graphs for a problem like this since it's such a complex equation, I went ahead and wrote this in regression form. In my regression video on the channel, you can see exactly how I did what I just did here. But basically what this would be is exactly this, just written in regression form. Okay, so the thing you may notice here, first of all, is that it says they're both equal to 0. We can just think logically, okay, it doesn't really make sense for the width to be 0. It's not like this is an imaginary rectangle. So we can just easily fix that by just saying W has to be greater than 1. Okay, now it's fixed and it gives us the right thing, which would be 10. So therefore the answer to this one would be 10. One last thing before we end off this video, and this is actually maybe surprisingly really important for these problems, is this thing involving scale factors for these different shapes. So I want you to think for a second, let's say you had a cube like this, and let's say each side of the cube is 2. And let's say you just multiply each side by 3. So now for this one, each side is 6. What did we do here? Well, we took each one and we multiplied it by 3. Each side, I mean. And now we just have a cube that is basically 3 times as big. But is it really 3 times as big? Not exactly. Yes, the sides are each 3 times as big. But let's say we were trying to find the surface areas of each one of these. If I found the surface area of this smaller cube, and I was trying to see what do I have to multiply it by to get to the bigger one, I would not just do 3, I would actually do 3 squared. So if we found that the surface area, actually I guess I can just find it. Okay, the surface area of the smaller one would be 24, so I can just go do 24 times 3 squared, and 216 would be the surface area of the bigger one. Now you can probably get what I'm about to say next, volume. For the volume of these shapes, it would be the same thing, except now we would just cube it rather than square it, so do the 3 exponent. The volume of the smaller one is going to be 2 times 2 times 2, so that would be 8. So I would just do 8 multiplied by 3 to the third. It is also 216. Do not worry, that is not on purpose. That's just a random coincidence that they both end up being 216. It is not always going to be the exact same amount. So that is how this works. I also wrote just a simple explanation here. If you have a cube that's doubled, the volume will increase by either 2 squared, or 2 cubed. And for this one, it would increase by 8 if you're trying to find the volume specifically. When you see a problem like this, the way you always think about it is what is the linear scale factor, aka what would be that 3 number like for this problem or the 2 for here. And then once you find that, you can just use that number to solve everything else involving the problem. Okay, let me show you an example here that's really good. So 2 right square pyramids, again, back to the pyramids, they are now similar. In case you're curious, what similar basically means is just exactly this. They would be taking the exact same thing, just multiplying it by a certain amount to get to the bigger one. And they say the ratio of specifically the surface areas of them is 9 to 25. So if the surface area of this one is 9, the one of this is going to be 25. And then if the volume of the small period is this, what is the volume of the larger one? Okay, the first thing we were trying to do, like I said before, is trying to find what would be the linear scale factor, aka what would we have to multiply each side by for this one to get to the bigger one. We have this 925 thing. It's kind of a confusing way to write this, but let's think what would that really be saying here? Basically, it's saying if we have 9 as the surface area for the first one, we would have to multiply it by some random number, let's just call it L, to get to 25. And so that random number would be 2.777. So that essentially would be the scale factor for the area. Keep in mind, this is the area, not the regular size that are being changed here. So we're kind of going backwards now. We don't have the linear scale factor, we just have the area scale factor right now. Then with this information, I can just go ahead and take this, and then I can just say that must be equal to the actual linear scale factor, let's say S squared. And so that, therefore, the actual thing we're doing for the linear scale factor would be 1.67. So that is the actual linear scale factor for this problem. Now, based off that, we can find everything else we need to know. This squared would be the area scale factor, and then this cubed would be the volume one. So for this one, it says 270 for the smaller ones. So we can just do 270 multiplied by, I guess I can just say S cubed. And so that gives us 1250, basically, you know, a little bit of rounding stuff here, but 1250 for the answer for this problem, which would be C. Keep in mind, I went over a bunch of problems in this video, and this video was probably fairly long for you watching it, but this is really only a snapshot of what can appear in area and volume problems. There's a ton of different stuff that can show up for these problems, a ton of different ways you can ask questions. You know, you can think of all kinds of unbelievable ways to ask new area and volume questions. So you will need to do practice with this to really understand what is going on here, to be honest. Now, if you want some of those practice problems, and also if you want the chance to improve your score over 100 points before your next test, check out Mission 1400 Plus with the link in the description below. You're going to be taken to a page that looks a little bit like this. And what we do is we actually help students break from below 1400 to higher than 1400 within a short time frame. If you join, you're going to get my full math course and full reading and writing course, an 8-week roadmap that's fully gamified on everything you need to do to prepare for the test, plus also a credit system that a lot of students really like, where they can actually study and earn rewards for preparing for the SAT. So it's really cool, really awesome. Would really recommend joining if you have the chance to. We have a free trial, so you can join 7 days with no risk. Anyways, good luck on the SAT. I'll see you in the next video, and make sure to always stay Gucci.